Hi, hello guys. Let's understand the degrees of freedom in engineering. In engineering, understanding how a system can move or change is the key to analyzing it correctly. In this video, we will break down the degrees of freedom in a simple and practical way with clear examples you can actually relate to. Defining it, degrees of freedom represent the independent variables solved in an engineering model. What are independent variables? They are the quantities that can change freely without depending on other variables. Examples are displacement, rotation, and temperature. We can say that if you want to displace from one place to another, you don't have to depend on any other variable like rotation. It is an independent one. Okay. On all these images will be clear to you when I teach the upcoming slides. And this is the 6 degrees of freedom for a ship, and this is for our head, which has a 3 degrees of freedom. Okay, the degrees of freedom will tell how many choices a system has to change its state. Fine. If it has more choices, mean it has more degrees of freedom. That's all. Let's say for degrees of freedom of a point in 2D space. Let's say this is the graph. This is two-dimensional one, right? Like this is not three-dimensional. The graph x and y. There are only two axes. Let's start with the simple case. A single point in a planar two-dimensional space. That is this graph. Assume we have fixed a point origin and a standard coordinate system. Here, to look at any point in this plane, we need exact two pieces of information. Correct? So let's say the point. Let's take the blue point. It is from the x-axis. This is x minus 3 and y. In y it is 2. So minus 3 comma 2, the distance from origin along x and y axis, right? A point in a 2D space therefore has 2 DOF. That's all. It needs two parameters to define the position of this point. So so the point has 2 DOF. Two independent translation. Translation means moving. Okay? And it can't rotate because a single point has no orientation, right? Like so it can't rotate. So this is clear. Yeah, and here the next thing is the rigid triangle in 2D, which is adding rotation. Yes, there are two triangles here, right? Why there is 3 DOF? Now observe the orientation. The red and blue triangles are tilted differently. Yes, this change cannot be explained by x and y translation alone. In a 2D plane, the rotation is possible only about one axis. Correct? The axis perpendicular to the plane. Here the plane is xy. Perpendicular to it means the z axis that is coming out of the screen. What you are seeing. This rotation is considered and denoted by using the symbol theta. So rotation about the z axis is 1 DOF. So yes, like why the rotation is considered? Because a red or blue color triangle, it can be rotated, right? Like it can be rotated in 0 degree, 90 degree, 30 degree. So to define it exactly, we need 3 DOF. Translation means what I said, moving along x, along and along y. So 2 DOF in translation, and in rotation, there is an about the z axis. So this triangle, each triangle will have 3 DOF here. Fine. And the next one, a point in 3D space, just a point. Let's say this. Let's consider this box as it has 3 axes. It is a 3-dimensional space. Here, a point in 3D space has 3 DOF. It has 3 independent translation. We are considering only the point. In the diagram, it shows us rotation. A point cannot rotate. X, Y, Z. Like these coordinate system is what we need to define a point. So this a point in 3D space will have 3 DOF. Right? And the next thing, a rigid body in 3D. Like we are having a box. Within this, we put a toy. If we put a toy inside the box, the toy can rotate. Correct? A rigid body in 3-dimensional space represents most general case and exhibit the maximum possible degrees of freedom. Let's consider a solid object, that's a toy, or a line segment, a line with points A and B connected rigidly. It can translate means move freely in any direction and rotate about any axis. Right? Consider a box. If a toy can move XYZ axis, and also it can rotate about XYZ axis. Right? Like if it rotate about x-axis, it is roll, pitch. Yeah, these are aeronautical terms. Yeah, and here it will have 6 degrees of freedom. That is 3 translation plus 3 rotation. This is the maximum degrees of freedom any rigid body in 3D space can have. In the real world DOF examples we can take, understanding DOF become intuitive really when you connect it to everyday objects, right? Like so, the common things are, let's say lift. It has only one DOF because it can move only up and down, and the sliding door only horizontal translation. Lift will have vertical translation. A car on road, it can move about any 3 axis, the steering. So it has 3 DOF, 3 translation ones. A drone in air, complete freedom. It can rotate in 3 axis and it can also translate, move in 3 axis. Yes, and you can read the definition here as I already said. So now it will be much easier for you to understand this now. Let's take a ship or a boat. It can move and it can also rotate. Alright, like so this has 6 degrees of freedom. Thank you. Hope you understand.